Ever wonder how chemists figure out what molecules actually look like? Well, today, we're basically becoming molecular detectives. We're going to learn how they can take some unknown substance and draw a complete map of its structure, right down to the last atom.
And that's a really good question, right? I mean, molecules are so tiny you can't just stick them under a microscope. So, how in the world do you map something you literally cannot see?
Well, the answer is this amazing technique called NMR spectroscopy. Honestly, you can think of it like a GPS just for the hydrogen atoms or protons inside a molecule. If we can figure out where all the hydrogens are, we can put together the whole puzzle. So let's get to it and start gathering our clues. All right, here's our game plan. First, we need to understand the map itself. Then, we'll collect 3 critical clues: where the protons are located, how many of them there are, and who their neighbors are. And once we have all that, we'll put it all together to crack the case and ID a mystery molecule.
So, you know every good detective has to know how to read a map. For us, that map is something called an NMR spectrum. And believe me, it tells us everything we need to know about the protons we're hunting down.
I really love this way of thinking about it. See, every unique proton, or, a group of protons that are all identical, sends out its own signal. And that signal is basically a report on its exact situation inside the molecule, what chemists call its chemical environment. So different environments, different signals. Simple as that. Okay, so let's get to our first big clue. And this one is super important. Where on the map does a proton signal actually show up? This position is called its chemical shift, and it's absolutely key to figuring out what's going on around that proton.
So this position, the chemical shift, it's measured in a unit called parts per million, or ppm for short. Think of it like a unique street address for each and every type of proton. But what actually decides that address?
Well, it all comes down to electrons. Just imagine electrons as these little tiny shields protecting the proton. So, if a proton is surrounded by a nice, thick cloud of electrons, we say it's shielded. Its signal will show up on the right side of our map, we call that upfield, at a low ppm number. But if something pulls those electron shields away, the proton becomes deshielded and its signal slides over to the left, or downfield, to a higher ppm number. And this is a perfect illustration of that map. Just look at the scale on the bottom there, going from 0 to 8 ppm. See, the signal's way over on the right, close to 0. Those are our cozy, well-protected, shielded protons. And the ones over to the left? Yeah, those are the exposed, deshielded guys. So, what's actually strong enough to pull these electron shields away? Well, the main culprit is something called electronegativity. You probably remember this from chem class. It's basically how much an atom likes to hog all the electrons in a bond. And wow, this shows the effect perfectly. Just look at this lineup of molecules. As we switch from iodine to bromine to chlorine, and then all the way to the super electronegative fluorine, watch what happens. The ppm value for the proton signal just keeps climbing. That fluorine atom is like a vacuum, just yanking all that electron density away, leaving the protons totally deshielded and shoving their signal way downfield. Okay, so clue #1 is down. We know where the protons are. Now for clue #2. How many of each type of proton do we have? You can think of this as taking a head count, like a little census of the molecule. This technique is called integration. What the NMR machine does is it measures the area underneath each signal. And here's the key. That area gives us the ratio of the protons for each signal. It's not the exact number, but the ratio is all we need to solve the puzzle. Take a look at this spectrum. You see those S-shaped red lines that go up over the peaks? The height of each of those steps is the integration value. So if one step goes up by, say, 2 units, and another step goes up by 3 units, that tells us the ratio of those protons is 2 to 3. It's such a powerful piece of information. All right, we've got their locations and we've got their numbers. The final clue. This one comes from the neighbors. Turns out protons are kind of nosy. They can actually feel the magnetic fields of other protons on the atoms right next door. And this little interaction, well, it causes their signal to split into multiple little peaks. And this whole thing follows a really elegant and simple rule. It's called the N+1 rule. A proton signal will get split into N+1 peaks, where N is just the number of protons on the carbon right next door. So let's say a proton has 2 neighbors. Its signal will be split into, you guessed it, 2 + 1, which is 3 peaks,
We call that a triplet. And this table just lays it all out so clearly. No neighbors, n is 0, so n plus 1 is 1. You get a single peak, a singlet. Got one neighbor, n is 1, so you get a two-peak signal, a doublet. Two neighbors gets you a triplet, three gets you a quartet. You see the pattern. It's like the protons are literally telling us who they're living next to. But here's what's just mind-blowing. The size of these little peaks, their intensity, follows a perfect mathematical pattern. It's Pascal's triangle. You can see it on the right. That triplet has peaks in a 1 to 2 to 1 ratio, and the quartet is 1 to 3 to 3 to 1. It is just so cool. It's one of those beautiful moments where you see how elegant the rules of nature really are. Okay, detectives, we've got our 3 clues: chemical shift, integration, and splitting. Now it's time for the big finale. Let's put it all together and solve this thing. So, here's our mystery molecule, our suspect, tert-butyl methyl ether. We have its NMR spectrum right here, so now we just have to check if the evidence matches up. Let's see if the story it tells makes sense. All right, let's go through our checklist, clue by clue. First up, signals. Okay, in the molecule, we have those 9 identical protons on the big group on the left. That's one type. Then we have the 3 protons on the little methyl group on the right. That's a second type. So 2 types of protons should give us 2 signals. Let's look at the spectrum. Yep, 2 signals. Check. Second clue, integration. We've got 9 protons on one side and 3 on the other. That's a 9 to 3 ratio. Looking at the integration curves, yep, that matches. Check. Okay, final clue, splitting. Let's look at the 9 protons on the left. The carbon they're attached to is next to an oxygen and another carbon with 0 protons on it. So n equals 0, n plus 1 is 1. It should be a singlet, and it is. Now for the 3 protons on the right. They're next to an oxygen, so again, 0 proton neighbors. They should also be a singlet. And they are. Check. Okay, the evidence is undeniable. The number of signals, the ratio from the integration, and the fact that they're both singlets, it all matches our suspect perfectly. Case closed. This is what makes NMR spectroscopy such a ridiculously powerful tool for chemists. I mean, think about it. Just by using 3 simple clues, we figured out the exact structure of a molecule. And that's just from listening to what the hydrogen atoms have to say. It really makes you wonder, doesn't it? What kind of stories could other atoms, like carbon or nitrogen or phosphorus, tell us? It feels like the investigation is really just getting started.